Welcome back, everybody. In today's video, we're going to be covering LAN switching, and this is Ethernet within your local area network. In a later video, we'll cover how Ethernet travels from your local area network over the internet. But for this video, we're going to stay on the local area network. As a review, here's a slide from the OSI model showing the physical layer. The physical layer defines the physical characteristics of the medium used to transfer data between devices. For example, voltage levels, maximum transmission distance, physical connectors, cable specifications, etc. At the physical layer, digital bits are converted into either the electrical signals for a wired connection or the radio signals for a wireless connection. And all of the information from my video about cables and cable specifications is related to the physical layer. You may also remember this slide from the data link layer on the OSI model. The data link layer provides node-to-node connectivity and data transfer. For example, PC to PC, router to router, or switch to router. It defines how data is formatted for transmission over a physical medium. For example, copper UTP cables. It can detect and possibly correct physical layer errors. And the data link layer looks at the MAC addresses. And remember, switches operate at layer 2, the data link layer of the OSI model. The video today that you're watching is going to be focused mainly on layer 2, the data link layer. So what exactly is a LAN, or a local area network? Basically, a LAN is a network contained in a very small area. For example, your office building or the floor of your office building, and LANs are separated by routers. So going off our definition of a LAN, how many LANs do you think are in this photo right here? Well, there's 3. First, you have the LAN that we saw from the first slide when we started the video. Then the second LAN here down at the bottom, because like I said, routers are what separate a LAN from the network, not the switch. But as you can see from the side view here, you can have 2 switches connected to 2 separate ports on a router, which makes it a separate LAN all by itself. So we have 3 LANs in this photo. Now, even though in this third LAN we have 2 switches, switches are not what connects LANs, but a switch can be used to expand one LAN. So in this video, we're going to cover how information is sent within a LAN itself. So for example, from this PC through the switch over to this PC over here. So to quickly walk through the encapsulation process, if you remember, at the top 3 layers we have data produced, then that data is moved to layer 4, or a layer 4 header is added, and then the data becomes a segment. Then a layer 3 header is added, and the segment becomes a packet. And then a layer 2 trailer and a layer 2 header is added, and the packet is now a frame ready to be sent over the network. And if you remember, these are all called protocol data units, or PDUs. And so in this video, we're going to focus on how switches forward and receive frames. So here we see the Ethernet frame, which is a packet of an Ethernet header and an Ethernet trailer. The Ethernet header is made up of 5 parts. We have the preamble and the SFD. SFD, which stands for Start Frame Delimiter. This helps in synchronization between the devices. Next, we have the destination, or the layer 2 address where the frame is being sent. Next, you have the source, or the layer 2 address of the device that sent the frame. Next, you have type, which indicates the layer 3 protocol that is used in the packet, which is typically always going to be IP version 4 or IP version 6. However, sometimes this can indicate the length of the encapsulated data. It really just depends on the version of Ethernet. Now, the Ethernet trailer only has one field, and it's called the FCS, which stands for Frame Check Sequence. The receiving device will use this to check for any errors that may have occurred during transmission. So now let's take a closer look at the preamble and the Start Frame Delimiter. The preamble is made up of 7 bytes, which if you remember from earlier, 7 bytes equals 56 bits. Another way of putting that is this 1s and 0s alternating, or 10 10 10 7 times. And what this does is it allows devices to synchronize their receiver clocks so they can make sure that they're ready for the next bit of data that's coming through. Now let's look at the Start Frame Delimiter. SFD, if you remember, stands for Start Frame Delimiter. The Start Frame Delimiter is 1 byte long, which is 8 bits. It can be displayed as 10 10 10 11, similar to the preamble, except it ends in 1 and not 0. The Start Frame Delimiter marks the end of the preamble and the beginning of the rest of the frame. So now we'll take a closer look at the destination and the source fields. The destination and source fields indicate the devices sending and receiving the frame. The destination and source fields consist of the destination and the source MAC addresses. MAC address stands for Media Access Control, which is a 6-byte or 48-bit address of the physical device itself. The next field was the type field, or what sometimes can be the length field. This field is 2 bytes long, or 16 bits, and it can be either the type of data being transferred, or it can determine the length of the packet. And what I mean by that is if it has a value of 1500 or less, it indicates the length of the packet in bytes. However, if it has a value of 1536 or greater, that will indicate the type, usually IPv4 or IPv6 of the encapsulated packet, and the length can be determined in other ways. We'll get into more detail on how we come up with those values in later slides. So that covered all the fields in the Ethernet header. So let's review the sizes. The preamble was 7 bytes. The start frame delimiter was 1 byte. The destination was 6 bytes. The source was 6 bytes. And the type was 2 bytes. Now let's take a look at the only frame that is in the Ethernet trailer, the FCS or frame check sequence. The only field of the Ethernet trailer is FCS, which stands for frame check sequence. The frame check sequence is 4 bytes long, or 32 bits. The FCS detects corrupted data by running a CRC algorithm over the received data. CRC means cyclic redundancy check. So now that we've covered all the fields in the Ethernet header and the Ethernet trailer, let's go back over what sizes they are. We have the preamble, which is 7 bytes. We have the start frame delimiter, which is 1 byte. We have the destination field, which is 6 bytes. We have the source field, which is also 6 bytes. We have the type or length field, which is 2 bytes. And we have the FCS, which is 4 bytes. This gives us the total size of the Ethernet frame, which is 26 bytes. Now in this video, I'm mainly going to cover the source and destination MAC addresses from the source field in the Ethernet header. So let's go over what exactly a MAC address is. A MAC address is a 6-byte or 48-bit physical address assigned to the device when it is made. A MAC address is also referred to as a burned-in address, or BIA for short, meaning that the manufacturer burned it in as it was making the device. MAC addresses are globally unique. You should not be able to find 2 separate devices with the same MAC address. The first 3 bytes of the MAC address are the OUI, or Organizational Unique Identifier, which is assigned to the company making the device. So Cisco, for example, probably has a set of OUIs that are unique to Cisco themselves. And the last 3 bytes are unique to the device itself. And MAC addresses are written as 12 hexadecimal characters. So briefly, before we get into what a hexadecimal number is, we're going to cover what a decimal number is. In a decimal number, there's 10 possible digits between 0 and 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So they can be placed like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have to start over back with 1. And so what this means is that there's 0 ones and 1 10. So you got 10, 11, 12, 2, 4, 5, 6, 7, 8, 10. And you just keep going until you get to 99. So when you get to higher numbers like 100, what 100 means is 1 value of 100, 0 values of 10, and 0 values of 1. And it just keeps going until you get to 200 and 300 and so on. And that was a real simple, quick view of how the decimal system worked. So now we'll look at the hexadecimal system. Well, the hexadecimal system, you have 16 possible digits you can use. The first 10 digits are the exact same as from the decimal system. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the last 6 digits are borrowed from the alphabet. A, B, C, D, E, and F. So A is the same thing as 10, and B is the same as 11, C is the same as 12, D is the same as 13, E is the same as 14, and F is the same as 15. Here is a chart that I found doing a quick web search that shows the decimal number, their hexadecimal equivalent, and the binary form of that number. Now we've already covered up to from 0 to 15, but as you can see, it can keep going from 15 to 31 to 47, and it can keep going all the way up into the hundreds. Now if you notice, this hexadecimal number besides 16 looks like 10, but it's not really a 10. Instead, this is 116 and 0 ones, which makes it the equivalent to the decimal 16. And this hexadecimal 11 is really 116 and 1 1, which is the equivalent of decimal 17. And hexadecimal 1 2 is decimal 18. And as you can tell from the chart, hexadecimal keeps going 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, etc. This video is really just to give you an introduction to hexadecimals. We'll go more in depth into them in a later video. Here we have a small network, just 2 PCs connected with a switch. If you notice, the interface names on the switch, we have FO1 and FO2. FO stands for Fast Ethernet. So these are 100 megabits per second interfaces. I have also labeled the MAC addresses for the two PCs in the picture. Normally a MAC address is going to be a more random string of numbers and letters than this, but I made it simple for our walkthrough today. If you notice, each MAC address is a series of 12 hexadecimal digits separated by a period, and sometimes you'll see a period at the end of every other digit. For example, you may see AA.AA, but most of the time the decimal place will be at the end of every fourth character in the MAC address. The OUI, our organizational unique identifier, the first half of the MAC address, is AA.AA.A0 for each device. So both of these PCs are from the same manufacturer. But the second half of the MAC address is different for both PCs because the second half identifies the individual device itself. So in this example, the second half of the MAC address for PC1 ends in 01, and the second half of the MAC address for PC2 ends in 02. Now let's say PC1 wants to send some data to PC2. For simplicity, I'm just going to put the last couple of digits of the MAC address for PC1 and PC2 on here. This type of frame is called a Unicast frame, or a frame destined for a single target. In this case, PC2. PC1 sends the frame to the switch. Once the switch receives the frame, it looks at the source MAC address of the frame came from and uses that information to learn where PC1 is. As you can see from this table, switch 1 added the MAC address of PC1 to its MAC address table and labeled it as coming from interface F01. This is called a dynamically learned MAC address, or just dynamic MAC address, because it wasn't manually configured on the switch. The switch learned the MAC address itself. Every switch will keep a MAC address table similar to this, and the switch will fill the MAC address table dynamically by looking at the source address of frames that it receives. Since switch 1 received a frame from MAC address AAAA.A000.0001 and interface F01, it knows it can reach that MAC address by going back through interface F01. This is how switches learn where each device on their network is at, by looking at the source address of the frames that they receive. However, there is one problem. The destination MAC address is AAAA.A00000002, but switch 1 only knows of MAC address 001, interface F01. So switch 1 does not yet know where that MAC address is. This is referred to as an unknown unicast frame because the switch doesn't have an entry for the destination MAC address in its table. So this means that switch 1 will flood the frame. That means the switch 1 will send the frame out through every interface except for the one that it was received on. Flooding the frame will look like this. The switch basically copies the frame and sends it to every machine that is connected to it throughout every interface except for the one that it came out of. PC3 basically just drops the frame because the destination MAC address does not match its nation MAC address. However, PC2 receives the packet, sees that it matches this MAC address, and so it proceeds to process the packet normally up through the layers of the OSI model. However, unless PC2 sends a reply of some kind, the process stops there, and switch 1 still doesn't know which interface PC2 is technically on. So if PC1 sends another packet to switch 1, since switch 1 still doesn't know what interface the destination MAC for PC2 is on, it floods the packet again, sending it to out every interface that it has except for the interface that the packet was received on. And again, PC3 drops the frame because it's not destined for his MAC address, and PC2 sees that it matches this MAC address, so it processes the frame as it normally would through the layers of the OSI model. Let's say PC2 now wants to send a response back to PC1. If you look at our frame in the image, the destination and source MAC addresses have switched. So now the destination MAC address is PC1 and the source MAC address is PC2. PC2 is first going to send that frame to the switch. That switch is going to look at the source MAC address on that frame, and it's going to see that it doesn't already have it in its MAC address table. So this time it's going to put the MAC address of PC2 in its MAC address table. It's going to put MAC address 02 was on interface F02. And then it's going to look at the destination MAC address, and it's going to see that it already has the destination MAC address in its MAC address table. 01 is on interface F01. So switch 1 is going to send that packet out interface 1 to PC1. This is called known unicast frame, where the switch already knows where the frame needs to go and it doesn't flood the frame out all interfaces because it already had the destination in its MAC address table. So keep in mind, unknown unicast frames are flooded because the switch doesn't know where they're supposed to go, but known unicast frames are forwarded to their destination because their destination is already in the MAC address table on that switch. One thing to note about the MAC address table is that on Cisco switches, dynamically learned MAC addresses are removed after about 5 minutes of inactivity. So if PC1 or PC2 don't send any network traffic in over 5 minutes, switch 1 would have to flood the next packet to either one of them, because their MAC address will no longer be in switch 1's MAC address table. However, if they were to send data again, switch 1 will again dynamically learn their MAC addresses. So let's expand our network a little bit, and this time we have 2 switches, and we have 2 separate MAC address tables. Currently the MAC address tables are empty, so we're going to walk through the process of frame forwarding and flooding again. So PC1 wants to send some data to PC3. The source MAC address on the frame is 01 and the destination MAC address on the frame is 03. So PCA sends the frame to the switch 1. Switch 1 learns PC1's MAC address by looking at the source MAC address on the frame, and then switch 1 puts that MAC address in its MAC address table along with the interface that it received the packet on. On a real MAC address table, you'll have the full MAC address. Here, I'm just writing it in a short form to keep things simple. And if you recall, a MAC address learned in this way is called a dynamically learned MAC address, or a dynamic MAC address for short. So right now, since switch 1 does not know where PC3 is, this is called a unknown unicast frame. So remember, a switch will flood an unknown unicast frame out every interface it has except for the interface that the frame was received on. So switch 1 in this case will send the frame out F03 and F02. When PC2 receives the frame, since it's not destined for its MAC address, it's going to drop it instantly. Switch 2, however, when it receives the frame, sees that it doesn't have that MAC address in its MAC address table already. So it puts PC1's MAC address on interface F03 for switch 2 in its MAC address table. So switch 2 just dynamically learned about PC1. So switch 2 received a unicast frame, so a frame that is destined for a single interface. But right now switch 2 does not know which interface the destination MAC address can be found on. So this frame, even though it's on switch 2, is still an unknown unicast frame. And what do switches do with unknown unicast frames? It floods the frame out every interface except for the interface that it came in on. So switch 2 sends it out interface F01 and F02. And PC4 drops the frame immediately because it's not destined for its MAC address. But then PC3 looks at the frame and sees that it's destined for its MAC address, so it processes the data up through the layers of the OSI model. Let's say PC3 now wants to respond to PC1. So it's going to change the destination MAC address to PC1 and the source MAC address to PC3 in the frame. So PC3 sends the data to switch 2. Switch 2 looks at the frame, it sees a new MAC address, so it adds that MAC address to its MAC address table, and it puts 03's MAC address coming from interface 01. And it sees that it already has the destination MAC address in its interface table. So this frame is what's called a known unicast frame. And what do switches do with known unicast frames? It forwards the frame out the interface that it already has for 01, which is interface F03, to switch 1. Switch 1 receives the frame, sees the new MAC address for 03, and it sees interface F03, so it adds those to its MAC address. And switch 1 already has an entry in its MAC address table for PC1, so it forwards the known unicast frame onto PC1. Okay, so that was a lot of information, so I thank y'all for hanging in there with me. If you found this information useful, be sure to hit the like button and the bell icon and then subscribe so you'll know when future videos come out. And there's a link down below to the slides that were used in this presentation.